G'day again. Welcome back to Mathematics 302. Hope you're having a good morning or a good evening. A little bit of humour. This is take, I don't know, 27 of this video. Just trying to get this one right. Uh, anyway, hopefully you get it right this time. Okay. Hope you're enjoying yourself. Okay, right. Lecture 1, Part C, take 27. Okay, we're going to do functions and De Morgan's law. Hopefully right this time. Let's go. Okay, function, and you've got to try and stop laughing. The function is a bounded set. Uh, a function of a bounded set is where the set of output values are also bounded, staying within a limited range. So this is like limits in high school. And you would have certainly seen these graphs. So y equals cos x and y equals sin x. They're obviously bounded by 1 and minus 1. So they're bounded above and bounded below. Breathe. So y equals 10x, that's not bounded. We're looking at the y value there. So what is the range? So the range is unbounded. It goes up and down, forever and ever. Look at another one. So y equals x squared. We can see that that's obviously not bounded above but bounded below. And then y equals x cubed. My picture's in the way, but I'm not going to move it. So that's just unbounded. Okay, so that's just your basic functions. You should be aware of that sort of thing. Not necessarily using the word bounded and unbounded, but certainly of the shapes of those sorts of graphs. So if we just give some simple function questions, determine whether the following functions are bounded above, bounded below, bounded or unbounded. Let's go through them. So y equals 32 is bounded above and below since it's just a horizontal line. Y equals 2 to the x, that's an exponential graph. So that's bounded below by the x-axis because it doesn't really matter how small you make this x, how negative you make it, it's still just going to be a fraction. So it doesn't actually get to the x value of 0. It doesn't actually, sorry, get to the x-axis, which is the y value of 0, and it's unbounded above. Y equals 2 minus x squared, that's an inverted parabola with a vertex at 2, 0, and thus it's bounded above and unbounded below. Y equals the square root of 1 minus x squared. Obviously, you know that within a square root, this cannot be negative. So obviously, the greatest value of this can be 1. So this is the upper part of a circle, which you've probably certainly seen in high school with a radius of 1. So that's bounded above and bounded below. And last one, a little bit more tricky. Y equals x cubed square root x plus 4. So obviously this x value cannot be anything less than minus 4. So minus 4 will give you a 0. So you want to find bounded, but you can see it's not bounded above. X cubed will just go up infinitely. My image is, I'll just move that up there for a sec. It's bounded below. If you try x equals minus 3, that'll give you a 1 in there, and x equals minus 3.999. You might get to see how that graph actually skews a bit as it goes in between minus 3 and minus 3.99, but it's not bounded above because that x cubed goes up exponentially. Okay, so just some simple ones there. De Morgan's law. So the second part is De Morgan's laws. So De Morgan had two laws, very clever fellow. It relates the intersection and union of sets through the complement of the two laws. So the first law, law 1, states that the complement of the union of the sets A and B is equal to the intersection of their complements. So if you go A union B, find out what A union B is, take the complement of that, that's going to equal A complement intersection with B complement. And you can try that out. In fact, we will. And the second law is, what? Image in the way. Second law is that the complement of the intersection of sets A and B is equal to the union of their complements. So A intersection B, complement of the whole thing, equals A complement union with B complement. Okay, hopefully that sinks in. If it doesn't, this will help. So De Morgan's laws can also be represented with Venn diagrams, and visual images are great in maths. So here's a Venn diagram. A union B, complement. So there's A union B there. Complement of that is all of the green area. and that equals A complement intersection with B complement. Secondly, let's do the other one. A intersection B complement will be all of the green area again, and that will equal A complement union with B complement. Now, these two laws are, instead of calling them 1 and 2, which is, I think, the best way to refer to them, they can be referred to as this is the law of union and this is the law of intersection. Now, when they're referring to that, they're looking at the elements that are in the brackets. So A union B is in the brackets, A intersection B over here is in the brackets. So just be careful if you're naming them De Morgan's law of union, because both of these have both symbols. So you could accidentally write A complement intersection B complement and say, oh, this is the law of intersection. So just be careful that the laws are where they're labeling them with the words are referring to what's in the brackets. So I tend to favor law 1 and law 2 because then it's simpler. But this might help you in your memorization of De Morgan's laws. So let's do a question on De Morgan's law. It's fairly straightforward. It's like a simplified way of doing a proof. So let U equal 1, 2, 3, 4, 5, 6, 7, 8, and A equal 3, 4, 5, and B equal 4, 5, 6. Prove De Morgan's first law using that information. I.e., we're going to show A union B complement equals A complement intersection B complement. So it's a fairly straightforward type of proof. I'm going to shrink that, put it up the top, so we've got a bit of space, and here we go. So we're just going to do left-hand side first, and then right-hand side, and what we'll find is the left-hand side equals the right-hand side. So left-hand side, so we're looking at A union B complement of the whole lot. So A union B, we've got A is 3, 4, 5, union with 4, 5, 6. So we're just going to combine those straight away. So we're going to get 3, 4, 5, 6. Obviously, when you're combining in union, you don't duplicate things in sets. Hence, A union B complement, the complement of 3, 4, 5, 6 is 1, 2, 7, 8. So we're looking at the complement within U. So they're the ones left over, and that's the left-hand side. So we're at that stage. We've got 1, 2, 7, 8. So now let's look at the right-hand side. So we're going to look up here at A complement intersection B complement. So what is A? 3, 4, 5. Well, the complement of A is 1, 2, 6, 7, 8. We're going to do the same for B. So B is 4, 5, 6. What is the complement of 4, 5, 6 in here? Well, everything else. So B complement is 1, 2, 3, 7, 8. So now we're going to look at the intersection of these two. So therefore that's 3 dots. Just as a reminder, in case you haven't seen it, the 3 dots are therefore. Therefore, what are they there for? Too many laughed. Okay, therefore, A complement intersection B complement is 1, 2, 6, 7, 8 intersection with 1, 2, 3, 7, 8. And we're going to get 1, 2, 7, 8, which is what we had up here. So now we've got the left-hand side equals the right-hand side, and therefore A union B complement equals A complement intersection B complement is proved. And that's pretty much as simple as it is whether you're proving the first law or the second law. It's really just going through the motion of labeling each of them, joining them together, doing the complement, etc., etc. Could make it more confusing possibly if you're using different letters or if you're just using single letters. But if you're doing it with full sets, it's fairly straightforward, and I think you're pretty confident to do that. That's it for this lecture, for the third one. Actually, I want to show you the basic identities question. So this is a question you'll get to do with basic identities. So if you write, and this is how they've included algebra inside of set theory, which is quite an interesting term. So let's go A multiplied by C plus A B complement C brackets plus B complement C. So they're giving you this algebraic question and saying simplify using basic identities. And the first question you're probably asking is, what the heck are basic identities? So let's just look at this algebraically as a first step and go, okay, can we simplify this? Yes, we can. Let's take out C. So that's just using basic algebra. We've got AC, the C comes out. Now we've got 1 plus AB complement. And you're thinking, okay, now I'm stuck. Now we're going to use the basic identities. And there is literally only one basic identity, which is this. If you've got A, so ignoring B and C, if you've got A plus A complement, and all there is A, that's the only set there. Well, A plus A complement, I mean, even if there is A, B, C, D, E, F, G, A complement is everything else. It's all of this plus all the outside, it's everything. So A plus A complement is regarded as 1, or it's regarded as U, the universal set, i.e. everything. Okay, so if you get A plus A complement, it's 1. If you get B plus B complement, it's 1. C plus C complement, it's 1. It's the universal set, everything. Likewise, and here's the interesting thing, what is A complement plus 1? Because 1 here is the universal set. Well, if you've got A complement, it doesn't really matter what you've got. If A complement is the rest, 1 is everything. 1 is the whole lot. So A complement plus 1, again, we're in set theory. We're not doing mathematics with normal maths. If you've got two sets, one is A complement and one is the whole universal set, you join them together, you're just left with the universal set, or 1. Okay, so here we can look at this and say, well, I've got 1, or the universal set, plus AB complement. Well, I don't really care what this is because I've already got everything. And 1 plus whatever is still the whole universal set. So we can simplify this by saying, well, I can apply this basic identity rule to say, well, that is just 1. That is in set theory, that is just 1. Or you could write U. So 1 plus that is just 1. And that's what it means to simplify using basic identities. It's just really using these two rules, I guess you would say, which are the basic identities of algebra within set theory. So now you've got AC plus B dash C. You can take the C out and you can get A plus B dash C. And there we go. So that's using basic identities question. These are pretty much the only basic identities you really need to be aware of. There is 2 questions there for revision. So I've put this question in. This is really a high school question, but I put it in because we're doing Venn diagrams. You can have a bit of fun with doing that. The rest of them are not so much fun. They're more important. So you've got using cardinality and power sets. Then you've got whether it's bounded or unbounded. Then here's using basic identities. And question 5 is just proving De Morgan's first law. Okay, that's it for this week. God bless you. Stay safe. Bless somebody else this week. Do something nice for somebody else. It's really encouraging when you do that. That's a really positive thing to do. So try and bless somebody else this week with in something, a smile, anything. Okay, God bless you. I'll see you next time. Bye.